It's Paul with the last and easiest of the 3 videos for the snowy day of February 9th. This is just a lead-in to Laplace transforms, which will be the subject of the next lecture, and it reviews the technique for solving second-order equations with constant coefficients that's taught in most physics courses. So instead of letting a, b, and c be coefficient functions, we will regard them as real constants. And in that case, the easiest way to solve the equation is to plug in a trial solution of the form y equals e to the rx. That's guaranteed to lead to the quadratic equation ar squared plus br plus c equals 0. So let's try this out on a very simple case. Y double prime minus y prime minus 2y equals 0. Plug in our trial solution. It's easy to differentiate that any number of times. The second derivative is r squared e to the rx. Y prime is r e to the rx, and y, of course, is 2 e to the rx. Since e to the rx is different from 0, we can safely divide by it. We get the quadratic equation r squared minus r minus 2 equals 0, which factors neatly into r minus 2 times r plus 1 equals 0. So the roots are r equals plus 2, r equals minus 1, and the kernel of the equation is spanned by the 2 independent solutions, y equals e to the 2x and y equals e to the minus x. You can plug them in and try them out for yourself if you like. But there's a case we have to worry about. Sometimes a quadratic equation has only a single real root. The rule that's taught for dealing with this case in a physics course is if you've lost a solution, multiply the solution that you found by the independent variable, plug it in and try again. It's guaranteed to work. We have a more principled way of dealing with this, though, because we know, given a second-order equation, how to find its Wronskian, and we know, having found the Wronskian and having one solution, how to find a second solution. So let's try out that technique. To get a double root, I'll use the quadratic equation, the differential equation, y double prime minus 2k y prime plus k squared y equals 0, because that is going to lead to a quadratic equation r minus k squared, which will have a double root. Having found one solution, I will use Abel's formula for the Wronskian, and then I will use the Wronskian to find a second solution. Let's try a specific case. Y double prime plus 4y prime plus 4y equals 0, and I'll choose as initial conditions y of 0 equals 1, y prime of 0 equals minus 1. So I plug in my trial solution to the equation. Y double prime, of course, gives r squared e to the rx. 4y prime is 4r e to the rx. 4y is 4 e to the rx. Cancel out e to the rx, it can't possibly be 0, and get the expected quadratic equation, r plus 2 quantity squared equals 0. That has r equals minus 2 as a double root. Okay. Well, to find the Wronskian, we need to form the antiderivative of minus b of x over a of x. But in this equation, b of x is the constant 4, a of x is the constant 1. So to get the Wronskian, we integrate minus 4 with respect to x, and the Wronskian of the two solutions is e to the minus 4x. Now that we've got that, we've got our formula for the second basis vector for the kernel, f2 of x. We take f1 of x, which we've already found, and integrate the Wronskian over the square of the solution already found with respect to t. So f1 of x is e to the minus 2x. The Vronsky is e to the minus 4x. f1 squared is e to the minus 4x. And I really should have written t's instead of x's here, but I'm not going to restart the whole video in order to do that. The answer is, the second solution is x e to the minus 2x. Multiply by the independent variable. Suppose we want to satisfy our initial conditions. We say our general solution is therefore some constant a times e to the minus 2x plus some other constant times our second independent solution, x e to the minus 2x. The second solution is 0 when y equals 0, so knowing that y sub 0 equals 1, we immediately discover that a must equal 1. It's easy enough to differentiate this solution. We get one term from differentiating a e to the minus 2x, and two terms from differentiating the product bx e to the minus 2x. We're told that y prime of 0 equals minus 1, and therefore minus 1 is equal to minus 2a plus b, plugging in x in the general solution. So b is minus 1 plus 2a, since we already know that a equals 1. b is also equal to 1, and we've got the solution to our initial value problem. Y of x equals 1 plus x e to the minus 2x not only satisfies our equation, it satisfies the initial conditions. Those of you who've studied classical mechanics may have encountered this situation before in considering the motion of a so-called critically damped oscillator when no external forces applied. This is the boundary between the situation where the mass just gradually settles down to rest at the origin and the one where it oscillates back and forth. Well, what else can happen with a quadratic equation? The last thing that can happen with a quadratic equation is it's got no real roots at all. It's got complex roots. In that case, the trial solution works just fine. You can get two solutions involving complex exponentials, or as you'll see in a minute, you can take one of those two solutions and say, if a complex valued function satisfies the equation, then the real and imaginary part separately must satisfy the equation. So as a concrete example, let's solve y double prime plus 2y prime plus 5y equals 0. Plug in the same old trial solution. Taking two derivatives multiplies by r squared. Taking one derivative multiplies by r. Taking no derivatives multiplies by 1, and there is the result of plugging in our trial solution. Cancel out the e to the rx. Again, we get a quadratic equation. R squared plus 2r plus 5 equals 0. I'll solve that by the quadratic formula. Minus b is minus 2. B squared minus 4ac is 2 squared minus 4 times 5, or 4 minus 20. How convenient. The square root of minus 16 is plus or minus 4i, and we find that r equals minus 1 plus or minus 2i. So we have two complex solutions, either e to the minus 1 plus 2i times x, or e to the minus 1 minus 2i times x. But we can perfectly easily get independent real solutions by using Euler's famous formula, e to the ix is cosine x plus I sine x. So our first complex solution can be written as e to the minus x times e to the 2ix. Replace e to the 2ix by cosine x plus I sine 2x, and the real part is e to the x cosine 2x. The imaginary part, where I drop the I, is e to the x times sine 2x. These are two independent real-valued functions that solve this equation. Next time, we will see how to generalize this technique by using Laplace transforms.